All right. We're going to talk about half-lives. We're just going to take some notes here on half-lives. If you have a substance that is radioactive, that means that it's falling apart, right? And a substance that is falling apart means it's mutating into something else. So we have right here, we talked about earlier, I've got some strontium 90, or I've got some cobalt 60, right? And if we do this, and it makes the Geiger counter fall off, we know that this cobalt 60 is mutating into nickel 60. Does that make sense? Right? We know it's happening because we can hear the Geiger counter go off. So, cobalt 60, we know some numbers for it. One of the numbers we know for cobalt 60 is we know the half-life of it. All right? And the half-life of something that's radioactive or falling apart is the amount of time it takes for half of it to fall apart. Okay? So, there's some simple math that we like to do with this. Now, how do we use half-life? This is one of the most important things that we use half-lives for, and that is carbon-14 dating. We saw a video yesterday on this guy. Anybody remember what he's called? Begins with a K. Kennewick Man. Okay? And this is Kennewick Man. Anybody at home, you can go to the slideshow and click on this, or you can just look at this video and type this in, or just YouTube Kennewick Man. Well, carbon-14 is an isotope of carbon, and it beta-negative decays. It beta-negative decays into nitrogen-14. Carbon-14 is found in your bones. If we look at your bones, we can see how long ago you died. Carbon-14 has a half-life of 5,730 years. That means when this guy died, he had a certain amount of carbon-14 in his bones. And then 5,730 years later, only half of that carbon-14 was left. And then after another 5,730 years, only half of that half was left. Does that make sense? So however much you have, half of that will disappear every 5,730 years. So this creates some interesting little math problems, right? When we think about doing half-life problems, we think about some of the problems with nuclear energy. We have a mountain we don't use, and we built this mountain to store radioactive waste because radioactive waste stays dangerous to humans for thousands and thousands of years. So we got that mountain, and we built a tunnel into it. It's called Yucca Mountain. We built a tunnel into it, and we said, hey, all this radioactive material from power plants, we're just going to go deep down in the earth and take it and put it at the very end of the tunnel, and then we're going to put some concrete over it. And then when we get some more, we'll take it in there, we'll bury it, and we'll fill up the middle of this mountain with this radioactive waste. But this radioactive waste is going to be surrounded by granite, thousands of feet in all directions. Does that make sense? So it can't possibly contaminate anything else. But we never used it. We spent $1 billion building it, and it's empty. Why is it empty? Politics. That's all I'll say. If you look at the United States of America, we have a map of all our nuclear power plants, right? If you look right here, there's a double circle right here at Southport because we have 2 nuclear reactors in Southport, which is how the lights are on. Does that make sense? Does that make sense to you? So, all of these places now are where our nuclear waste is actually stored because we're not using Yucca Mountain for political reasons. What do we do with the nuclear waste that is radioactive in Southport? When we're done, we take these nuclear fuel rods and we put them in a deep pool of water. That's it. If spent uranium, which is turned into thorium and other things, it's decaying, is underwater, I think it's like 20 feet of water, 10 to 20 feet of water. That's all it takes to block the radiation. Does that make sense? But still, this is not how we want to store this stuff. We need to come up with a better solution. That's all I'll say. Now let's go back and let's talk about carbon-14 dating and half-lives. All right? I'm going to give you a sample problem for us to work on. And I'm going to make the numbers easy. Okay? So we're going to think about Kennewick Man. And instead of saying 5,730 years, I'm going to just call it 6,000 years so the math is simple. Does that make sense? Because we're really just trying to understand the concept of half-life. All right? Let's start out here from the beginning. Let's say, my man, we dig up a dude, and we're like, yo, this guy looks very, very old. Okay? We take a sample of bone and we weigh it, and we know how much carbon-14 would be in that bone if he were alive. Okay? And let's pretend, and I'm trying to make up very simple numbers. Let's pretend if Kennewick Man was alive and we found his femur bone and we weighed it, that it should have 1,000 micrograms of carbon-14 in it. I'm totally making up these numbers. Okay? I'm making up simple numbers for us to use. So we find an old dead guy's leg bone, and we see how much it weighs, and we're like, hey, something with that should have 1,000 micrograms of carbon-14. And we know that the half-life of carbon-14, I'm just going to write HL, the half-life of carbon-14 is 6,000 years. Okay? We know this is true. What would happen? How old would this dude be if there was only 250 micrograms of carbon-14 in the bone when we tested it? Now we could brain this out. We don't even have to write down any math. We can just think about this. All right? If he started out with 1,000 micrograms, after 6,000 years goes by, how much should be left? 500. Because that's what we mean by half-life. It takes 6,000 years for half of it to disappear. Okay? Now that there's only 5, he's laying dead in the earth, right? Now, half of that will disappear in the next 6,000 years. So what's half of 500? 250 micrograms. So another 6,000 years has gone by. So if we dig up this guy's bones and it's only got 250 micrograms when it should have had 1,000, then we know this bro right here is 12,000 years old. That's how half-lives work. Does that make sense to you? Now, the last thing I'll tell you is things that are very, very old, we don't use carbon-14. Carbon-14 only works for things that are up to about 60,000 years old. After 60,000 years old, when it's gone through 10 half-lives, there's so little left that we can't recognize how to work the problem backwards. Does that make sense? We can't do that accurately. So when we dig up dinosaur bones and things like that, we don't use carbon-14. We use other ways to date those bones. And they're less accurate, but they go for further distances back in time. Does that make sense? Does that make sense? Last thing I want to show you before I cut the video off on is we got that guy right there. Since I made that slideshow, several of these guys have been found. These little woolly mammoths. And, I mean, look at this dude. I mean, he's still furry. And something that's this new, this one is 10,000 years old. How do we know? Carbon-14 dating. Does that make sense? So, carbon-14 dating is pretty darn accurate under 50,000, 60,000 years. That's a different one. So several of these have been found. Not all these are the same guy. That guy is obviously older. And a lot, why are we finding some of these woolly mammoths now? What's happening in the world that's allowing us to find some of these guys? Global warming. Well, yeah, climate change. Climate change is occurring. There's no debate about that. Some people that are maybe unscientific try to debate why climate change is occurring. But it is occurring. And glaciers are melting, right? And they're uncovering things like this that were trapped in the ice. So that's pretty neat.